The universe isn't just indifferent to our dreams of interstellar travel, it's actively hostile. Space is trying to end you in 47 different ways simultaneously. And I'm not exaggerating. Scientists have literally catalogued the threats: radiation, bone loss, muscle atrophy, cosmic rays. The list goes on. Can we overcome them? Are the stars forever out of reach? If you're into the science behind the dream, please subscribe to the channel. Now let's get started. The fastest spacecraft humanity has ever built is the Parker Solar Probe. As of 2026, it has reached speeds of approximately 190 kilometers per second during its closest approaches to the Sun. That sounds incredibly fast, right? It is by human standards. But at that speed, it would still take roughly 7,000 years to reach Proxima Centauri. 7 millennia, that's longer than all of recorded human civilization. The pyramids of Egypt were built roughly 4,500 years ago. Imagine a journey almost twice that long, and you begin to grasp the tyranny of distance we face. But here's where it gets interesting. Scientists and engineers around the world aren't giving up. They're developing concepts that could cut that travel time down dramatically. One of the most talked about projects in recent years is Breakthrough Starshot, a research initiative founded in 2016 by physicist Yuri Milner, cosmologist Stephen Hawking, and Mark Zuckerberg. The goal? Send tiny spacecraft called starships to Alpha Centauri in just 20 to 30 years. How would they do it? With light itself, Breakthrough Starshot envisions using a massive ground-based laser array, potentially spanning several kilometers, with a combined power output of up to 100 gigawatts. That's roughly the output of 100 nuclear power plants, all focused on a single tiny spacecraft attached to an ultralight sail. This sail would be incredibly thin, perhaps only a few hundred atoms thick, and made of advanced metamaterials designed to reflect light with extraordinary efficiency. The laser would push against this sail for just a few minutes, accelerating the craft to 15 to 20% of the speed of light. At that velocity, it could reach Proxima Centauri in about 20 years, send back data including images of any planets there, and give us our first close-up look at another star system. Sounds amazing, right? And it is. But as of 2025 and 26, reality has started to set in. Recent research published in June 2026 reveals challenges that weren't fully appreciated when the project began. Scientists Chao Shen and Jiaze Li from the Harbin Institute of Technology discovered that as these light sails approach relativistic speeds, meaning a significant fraction of light speed, they encounter a drag force from the photons themselves. This happens because of something called the Doppler effect. As the sail speeds away from the laser pushing it, the frequency of that light drops from the sail's perspective. Lower frequency means less momentum transfer, which means the faster you go, the harder it becomes to keep accelerating. It's like trying to run faster and faster, but the ground beneath you keeps turning to mud. And there's more. Another study from March 2026 by researcher Lucky Gangwa examined what happens when a spacecraft traveling at relativistic speeds encounters the interstellar medium. The interstellar medium, or ISM, is the stuff between stars. It's not empty space. It contains hydrogen atoms, dust particles, cosmic rays, and trace amounts of heavier elements. On average, there's about 1 hydrogen atom per cubic centimeter out there. That sounds like nothing, right? A near-perfect vacuum. But here's the cosmic joke. When you're moving at half the speed of light or faster, that near vacuum transforms into a deadly particle beam hammering your spacecraft. Gangwa's research reveals what he calls the magnitude paradox. While relativistic inertia helps keep your speed relatively constant across parsec-scale distances, the same relativistic effects cause extreme thermal loading on your hull. The front of your spacecraft faces energy deposition rates that no known passive material can survive. We're talking about temperatures that would vaporize steel, titanium, even advanced ceramics within seconds. This isn't a problem of slowing down, it's a problem of not melting. Think about that for a moment. You've solved the propulsion problem. You've built your laser array. You've accelerated your tiny probe to a fifth of light speed. And then the universe itself becomes your enemy, not because of some exotic danger, but because of simple hydrogen atoms hitting you so fast and so hard that your spacecraft turns into a fireball. Now, if you're thinking that maybe we should just send bigger, slower ships with people on them, I actually made an entire video exploring why generation ships, these massive vessels designed to carry humans across the centuries, face their own nightmare scenarios. The video is on the card above and pinned on the comments. The question becomes, if tiny probes face these challenges and generation ships have their own massive problems, what's left? This is where we need to talk about propulsion methods, because chemical rockets, the kind that took us to the moon, are completely off the table for interstellar travel. The physics simply don't work. To understand why, we need to talk about something called the rocket equation, formulated by Russian scientist Konstantin Tsiolkovsky in 1897. The rocket equation tells us the relationship between the mass of propellant, the speed of exhaust, and the final velocity of the spacecraft. For chemical rockets, the exhaust velocity is limited by the energy released in chemical reactions, which tops out around 4 to 5 kilometers per second. To reach even 1% of light speed using chemical propulsion, you would need a mass ratio so absurdly large that it becomes physically impossible. We're talking about needing a fuel tank billions of times more massive than the payload itself. You can't build that. The universe won't let you. So we need something better. We need propulsion systems that can generate far higher exhaust velocities or that don't rely on carrying propellant at all. Nuclear propulsion is one option that's been seriously studied since the 1950s. There are several variations, but let's focus on two main concepts: nuclear thermal and nuclear pulse propulsion. Nuclear thermal rockets heat propellant, typically liquid hydrogen, using a nuclear reactor. The hydrogen expands and shoots out the back at exhaust velocities around 8 to 9 kilometers per second. That's roughly twice as good as chemical rockets. Better, but still nowhere near what we need for interstellar travel. At those speeds, reaching Proxima Centauri would still take tens of thousands of years. Nuclear pulse propulsion, on the other hand, is far more extreme. The most famous concept is Project Orion, conceived in the late 1950s and early 1960s. The idea is shockingly simple and shockingly violent. You detonate nuclear bombs behind your spacecraft and ride the shockwave. A massive pusher plate absorbs the blast, and shock absorbers prevent the crew from being turned into paste. Exhaust velocities could theoretically reach tens of thousands of kilometers per second, potentially getting up to a few percent of light speed. But there's a catch, actually several catches. First, you need thousands of nuclear bombs. Second, you're leaving a trail of radioactive debris across the solar system. Third, the engineering challenges of building a pusher plate that can withstand repeated nuclear detonations are staggering. And fourth, there are international treaties that prohibit nuclear weapons in space. Still, from a pure physics standpoint, nuclear pulse propulsion could work. It's one of the few concepts we could theoretically build with modifications to current technology. Then there's antimatter. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into energy according to Einstein's famous equation, E equals mc squared. This is the most energy-dense reaction possible in the universe. A single kilogram of antimatter, combined with a kilogram of matter, releases roughly 43 million megajoules of energy. That's equivalent to the largest nuclear bomb ever tested. If we could harness antimatter propulsion, we could theoretically reach velocities approaching a significant fraction of light speed. Some designs suggest we could reach 10 to 20% of light speed, cutting travel time to nearby stars down to decades instead of millennia. But here's the brutal reality. We can barely make antimatter, and we definitely can't store it. As of 2026, humanity produces only a few nanograms of antimatter per year, primarily at particle accelerators like CERN. To fuel an antimatter rocket for an interstellar journey, we'd need kilograms, possibly tons. At current production rates, it would take billions of years to gather enough. And even if we could produce it, storing antimatter without it touching normal matter and exploding is an engineering nightmare we haven't solved. So antimatter, while theoretically perfect, remains in the realm of far future technology. Which brings us back to light sails and laser propulsion, the breakthrough starshot approach. The advantage here is elegant. You don't carry your fuel with you. The energy stays on Earth in the form of massive laser arrays, and you just carry the sail. This completely bypasses the rocket equation's tyranny. Your spacecraft can be incredibly light, just grams or perhaps kilograms, and the laser does all the work. The breakthrough starshot concept represents one of the most serious scientific attempts at interstellar travel we've ever made. But as we dig deeper into the physics, the challenges multiply in ways that are both fascinating and sobering. Let's talk about what happens during those critical few minutes of acceleration. Imagine a sail the size of a few square meters, weighing just a few grams, being hit by a laser beam carrying 100 gigawatts of power. The acceleration would be absolutely brutal. We're talking about forces reaching tens of thousands of times Earth's gravity. For comparison, when astronauts launch on a rocket, they experience maybe 3 to 4 Gs, 3 to 4 times Earth's gravity. Fighter pilots in extreme maneuvers might briefly experience 9 Gs. At 10,000 Gs, even the slightest structural imperfection would tear the sail apart instantly. This means the sail must be manufactured to tolerances we've never achieved before. We're talking about metamaterials, artificially engineered structures with properties not found in nature that can reflect 99.9% or more of the incoming laser light. Any absorption, even a fraction of a percent, turns into heat, and at 100 gigawatts, even tiny amounts of absorption mean the sail melts or vaporizes. Recent research in holography and diffractive sails, work advanced by visionary physicist Robert Forward before his death and continued by scientists like Greg Matloff, suggests a potential solution. Diffractive sails don't just reflect light like a mirror. They use microscopic optical structures, gratings etched at scales smaller than the wavelength of light itself, to manipulate how photons bounce off. This allows a flat sail to behave like a curved one, maintaining stability under the laser beam. Early tests, including the Alpha CubeSat currently in orbit as of 2026, are demonstrating these principles in space for the first time. But stability isn't the only problem. There's also targeting. The laser array on Earth needs to track this tiny craft as it accelerates away at an appreciable fraction of light speed. Within minutes, the spacecraft will be thousands of kilometers away. Within hours, millions of kilometers. The beam has to remain focused on a sail that, from Earth's perspective, is getting smaller and moving faster every second. This requires adaptive optics, systems that can adjust the beam in real time to compensate for atmospheric distortion, the sail's motion, and the growing distance. And here's something most people don't think about. Once you turn off the laser, that's it. There's no speeding up, no slowing down, no course corrections. You're on a ballistic trajectory for the next 20 to 30 years. If your aim was off by even a tiny fraction of a degree, You could miss your target star system by billions of kilometers. Now, let's imagine we've solved all of that. We've built the laser. We've manufactured the perfect sail. We've achieved 15% of light speed. The tiny star chip is hurtling toward Proxima Centauri, and it will arrive in about 28 years. What happens during those decades of flight? This is where interstellar travel stops being an engineering problem and becomes a survival problem. Space between the stars isn't empty. We already talked about the interstellar medium containing about 1 hydrogen atom per cubic centimeter, but there's more out there. Dust grains, tiny particles of silicate and carbon, ice-coated specks left over from ancient supernovae, float through the void. Most are smaller than a micron, a millionth of a meter. At rest, they're harmless. At 15% of light speed, they're bullets. When a dust grain, even one the size of a bacterium, hits your spacecraft at 45,000 kilometers per second, the kinetic energy is devastating. The impact energy scales with the square of velocity, so at relativistic speeds, even microscopic particles pack the punch of high explosives. A single grain could punch straight through your sail, your instruments, your communication array. Hundreds or thousands of impacts over decades would shred any spacecraft we could build today. This problem gets worse the faster you go. If we could somehow reach 50% of light speed, the energy of each particle impact increases by a factor of more than 11 compared to 15% light speed. At 90% of light speed, you're looking at impacts 36 times more energetic than at 15%. The interstellar medium transforms from a nuisance into an impassable barrier. Physicist Robert Zubrin, known for his work on Mars mission concepts, has pointed out that at very high relativistic speeds, spacecraft would need shielding on the order of meters of solid material just to survive the journey. But adding that much shielding defeats the entire purpose of a light sail, which needs to be as light as possible. It's a cruel paradox. The faster you want to go, the more protection you need. But the more protection you add, the heavier you become, and the harder it is to accelerate in the first place. Some proposals suggest using a sacrificial shield, a thin layer of material positioned ahead of the spacecraft that absorbs the initial impacts and slowly ablates away. Others propose using electromagnetic fields to deflect charged particles, though this does nothing against neutral dust grains. As of 2026, there's no perfect solution. Every option involves trade-offs that significantly complicate the mission. But let's assume we've solved the dust problem somehow. Maybe we're lucky, and the region of space we're traveling through is relatively clean. Maybe our shielding works better than expected. The spacecraft survives the journey and approaches Proxima Centauri after 28 years of flight. Now we have another problem. We can't stop at 15% of light speed. You're moving at roughly 45,000 kilometers per second. At that velocity, you'll cross the entire Alpha Centauri system in a matter of hours. You'll have a brief window, perhaps just minutes, to gather data, take photographs, measure magnetic fields, analyze the composition of any planets, and transmit everything back to Earth before you vanish into the cosmic depths beyond, never to return. This is called a flyby mission, and it's the only type of interstellar mission we can realistically attempt with current concepts. Stopping requires energy, and without carrying fuel, there's no way to decelerate. Some concepts involve using a second laser array at the destination to slow you down, or deploying a magnetic sail that interacts with the destination star's stellar wind. But these add enormous complexity and haven't been proven feasible, so we're left with a high-speed flyby. You get one shot, one chance to do all the science. And then you transmit your findings across 4.25 light-years of space back to Earth. Let's talk about that communication challenge, because it's just as daunting as everything else. Radio signals travel at the speed of light, So your message takes 4.25 years to reach Earth. But here's the problem: radio signals spread out as they travel. By the time your transmission crosses 4.25 light-years, it's spread over a sphere with a surface area of roughly 225 trillion square kilometers. The signal becomes incredibly faint, diluted across that vast area. To have any hope of Earth receiving your message, you need a powerful transmitter and a tightly focused beam. But your spacecraft weighs just grams. You don't have room for a large antenna or a powerful power source. Some proposals suggest using a small laser to send data back, which can be focused more tightly than radio waves. But that requires even more energy and precise pointing. And here's another layer of difficulty. Your tiny spacecraft needs power. Solar panels won't work once you're far from any star. Nuclear batteries, called radioisotope thermoelectric generators or RTGs, are what we use on deep space probes like Voyager and Perseverance. They generate electricity from the heat of radioactive decay, but RTGs are heavy and they degrade over time. After 28 years of flight plus 4.25 years for the signal to return, we're talking about a mission duration of over 32 years from launch to data reception. Your power source needs to last that entire time. The Voyager probes, launched in 1977, are still functioning as of 2026, nearly 49 years later. But they were much larger than a star chip, weighing over 700 kilograms each, and they've had to shut down instruments over the years to conserve power. A gram-scale spacecraft simply can't carry a multi-decade power supply with current technology. Breakthrough starshot researchers have proposed using tiny atomic batteries or even power beaming, where the Earth-based laser continues to send energy to the craft during its journey. But power beaming across light years is speculative at best, requiring the beam to remain focused on a target moving at relativistic speeds across interstellar distances. Every single aspect of this mission pushes the boundaries of what's physically possible. And we haven't even talked about navigation yet. How do you steer a spacecraft that weighs a few grams and has no fuel? You can't mount thrusters. You can't carry propellant. Some concepts involve using reflective surfaces that can tilt slightly, using the pressure of starlight to make tiny course corrections over decades. But these adjustments would be minuscule, and they require sensors, computers, and actuators, all of which add mass. The reality is that our first interstellar probes will likely be ballistic projectiles. We aim them as carefully as possible during launch, and then we hope our calculations were correct. Any errors compound over the journey, potentially causing the spacecraft to miss its target entirely. Think about the precision required. If your trajectory is off by just 1/1000th of a degree after traveling 4.25 light-years, you could miss Proxima Centauri by over 700 million kilometers. That's nearly 5 times the distance from Earth to the Sun. You'd sail right past the star system and never even get close. This demands navigation accuracy far beyond what we've ever achieved. The most precise spacecraft we've sent to other planets have done so using constant tracking from Earth, mid-course corrections, and gravitational assists from other bodies. None of those options exist for an interstellar probe traveling in a straight line for 3 decades. So we're faced with a mission profile that requires near-perfect execution at every stage. Construction, launch, acceleration, survival, data collection, and communication. One failure anywhere in that chain, and the entire mission is lost. Yet despite all these challenges, scientists haven't given up. Because the potential payoff is extraordinary, Proxima Centauri b, discovered in 2016, changed everything. For the first time, we confirmed an Earth-sized planet orbiting the habitable zone of our nearest stellar neighbor. The habitable zone is that precious region around a star where temperatures allow liquid water to exist on a planet's surface. and liquid water, as far as we know, is essential for life as we understand it. Proxima b orbits its star every 11.2 days at a distance of only about 7.5 million kilometers. That sounds incredibly close, and it is. For comparison, Mercury orbits our Sun at an average distance of 58 million kilometers, but Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun, producing only about 1/600th of the Sun's luminosity. So to be in the habitable zone, a planet needs to orbit much closer. This proximity creates its own set of challenges. Red dwarf stars are known for violent stellar flares, sudden eruptions of radiation, and charged particles that could strip away a planet's atmosphere over time. Proxima Centauri is particularly active, with flares that can temporarily increase the star's brightness by several times. If Proxima b doesn't have a strong magnetic field to protect it, the surface could be bathed in lethal radiation on a regular basis. We also don't know if Proxima b is tidally locked, meaning one side always faces the star while the other remains in permanent darkness. Many planets this close to their stars become tidally locked over time, just like our Moon always shows the same face to Earth. If Proxima b is tidally locked, one hemisphere would be scorching hot while the other freezes in eternal night. Life, if it exists, would have to survive in a narrow twilight band between these extremes, or rely on atmospheric circulation to distribute heat. But here's the beautiful part. We don't know. We can speculate, we can model, we can make educated guesses based on physics and planetary science, but we won't truly know until we go there and look. And that's why interstellar travel matters. That's why, despite every obstacle, scientists and engineers continue working on these problems, because we're not just talking about visiting another star, we're talking about answering one of humanity's oldest questions. Are we alone? The search for extraterrestrial life has been going on for decades through projects like SETI, the search for extraterrestrial intelligence, which scans the sky for radio signals from alien civilizations. So far, we've heard nothing but cosmic silence, but maybe we're looking in the wrong way, or maybe intelligent civilizations are rarer than we hoped, or maybe the distances are simply too vast for communication. Going there in person, or at least sending a probe, bypasses all of that uncertainty. Instead of waiting for a signal that might never come, we bring our instruments to their doorstep. We measure, we photograph, we analyze, and we know. And if we find even a single microbe, even evidence of ancient microbial life that went extinct millions of years ago, it would transform our understanding of the universe. It would tell us that life isn't a cosmic fluke, that the chemistry that produced us is happening elsewhere, that the universe is, or at least was, teeming with biology. But let's be honest with ourselves. The challenges we've discussed so far, propulsion, acceleration, dust impacts, navigation, communication, these are just the technical problems. If we ever want to send humans to another star, not just tiny probes, the difficulties multiply by orders of magnitude. Human biology wasn't designed for interstellar travel. We evolved on a planet with gravity, atmosphere, a magnetic field protecting us from radiation, and a 24-hour day-night cycle. Take any of those away, and our bodies start to break down. Astronauts on the International Space Station experience bone density loss, muscle atrophy, fluid shifts that affect vision, and immune system changes, even though they're only a few hundred kilometers above Earth's surface and only stay for months at a time. Now imagine decades or centuries in space with no gravity, constant radiation exposure, and no possibility of evacuation if something goes wrong. Radiation is perhaps the most insidious threat. In interplanetary space, astronauts are exposed to galactic cosmic rays, high-energy particles produced by supernovae and other violent cosmic events. Earth's magnetic field shields us from most of this radiation, but in deep space, there's no protection. A trip to Mars, lasting 6 to 9 months, would expose astronauts to radiation doses that significantly increase cancer risk. Now scale that up to an interstellar journey. Even at 10% of light speed, a trip to Proxima Centauri would take over 40 years. The cumulative radiation dose would be lethal without heavy shielding. And as we discussed earlier, adding shielding adds mass, which makes acceleration harder, which requires more energy, which makes the entire mission more difficult. Some propose using water or hydrogen as shielding, since those materials are effective at absorbing radiation and could potentially be used for other purposes like life support. Others suggest creating artificial magnetic fields around the spacecraft, a concept called a magnetic shield or mini-magnetosphere that deflects charged particles the way Earth's magnetic field does. But generating a magnetic field strong enough to protect a spacecraft and maintaining it for decades requires energy and technology we haven't developed yet. Then there's the psychological dimension. Humans are social creatures. We need community, variety, purpose, and hope. Locking people inside a spacecraft for decades with the same small group of individuals, eating the same recycled food, breathing the same recycled air, with no possibility of leaving and nothing to see outside but the endless black, would be psychologically devastating. Studies of isolated environments on Earth, Antarctic research stations, submarines, even long-duration space missions show that people develop psychological issues even under much less extreme conditions. Depression, anxiety, interpersonal conflicts, and cognitive decline all become more likely as isolation and confinement increase. Some researchers propose using suspended animation or cryogenic freezing to bypass the psychological and biological challenges. If you could put the crew to sleep for the journey and wake them up at the destination, you'd avoid decades of aging, radiation exposure, and psychological stress. It sounds perfect, but as of 2026, we can't do it. We can induce hypothermia for medical purposes, cooling people down for a few hours during surgery, but that's nowhere near the kind of long-term suspended animation we'd need. Freezing a human body causes ice crystals to form inside cells, rupturing cell membranes and causing irreversible damage. Some organisms, like certain frogs and insects, can survive freezing through specialized biological adaptations, but humans don't have those capabilities. There's research into suspended animation using chemical cocktails that slow metabolism without freezing, but it's extremely preliminary. We're decades, possibly centuries, away from technology that could safely put a human to sleep for years and wake them up healthy on the other side. So if we can't freeze people, and we can't shield them perfectly from radiation, and we can't prevent the psychological toll of decades-long isolation, what's left? This is why generation ships, those massive vessels designed to carry entire communities across the centuries, keep coming up in discussions of interstellar travel. The idea is that the people who launch won't be the ones who arrive. Instead, generations will be born, live, and die aboard the ship, with only the distant descendants finally reaching the destination. But generation ships face catastrophic problems of their own, which I explored in detail in my other video. The short version is that you need a genetically diverse population to avoid inbreeding, which means hundreds of people minimum. You need a closed-loop life support system that recycles everything perfectly for centuries, which we've never achieved. You need social and political stability across generations, which human history suggests is nearly impossible. And you need to maintain highly technical systems for longer than any civilization has ever existed, all while isolated in the void with no hope of resupply or rescue. The failure rate would be astronomical. Most generation ships would likely fail before reaching their destination through equipment malfunction, ecological collapse, social breakdown, or any combination of disasters. This brings us to a sobering realization. Interstellar travel, especially with humans aboard, might not just be difficult. It might be functionally impossible with any technology we can foresee in the next several centuries. But let's not end on despair, because there's another perspective here. Maybe we're thinking about this wrong. Maybe the question isn't, how do we send humans to other stars, but rather, how do we extend humanity's presence to other stars? What if instead of sending biological humans, we send our intelligence in other forms? Artificial intelligence, sophisticated enough to explore, analyze, and report back, could be far more resilient than biological life. AI doesn't need food, water, or air. It doesn't suffer psychological stress from isolation. It doesn't age in the same way, and it can be designed to withstand radiation and other hazards that would kill a human. Some futurists propose sending self-replicating probes, often called von Neumann probes after mathematician John von Neumann, who studied self-replicating systems. These probes would travel to a star system, gather resources from asteroids or moons, build copies of themselves, and send those copies to other star systems. Over time, even traveling at relatively modest speeds, these probes could explore the entire galaxy. The concept is theoretically sound. We already have the basics of three-dimensional printing and automated manufacturing. Scale that up, add sophisticated AI for decision-making, and you have a probe that could bootstrap an entire exploration network from raw materials. The idea of self-replicating probes exploring the galaxy raises a fascinating question, though. If this strategy is so effective, why haven't we detected probes from other civilizations? This is part of what's called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The Milky Way galaxy is roughly 13.6 billion years old. Our Sun and Earth formed only about 4.6 billion years ago. That means there were 9 billion years before our planet even existed, when other civilizations could have arisen. If even one of those civilizations developed self-replicating probes and sent them out, those probes should have spread across the entire galaxy by now, even traveling at just 1% of light speed. Computer models show that self-replicating probes could colonize every star system in the Milky Way in just a few million years. That sounds like a long time to us, but it's a blink of an eye in cosmic terms. Our galaxy has had billions of years for this to happen. So where are the probes? Where are the artifacts? Where is any evidence of advanced civilizations? Several explanations have been proposed. Maybe intelligent life is incredibly rare, and we're alone or nearly alone in the galaxy. Maybe civilizations destroy themselves before they achieve interstellar travel. Maybe there's some fundamental barrier we haven't discovered yet that makes interstellar travel impossible. Or maybe advanced civilizations simply choose not to expand, finding no compelling reason to spread across the stars. Each possibility is profound in its own way. If we're alone, then life and intelligence are precious beyond measure, possibly unique in the observable universe. If civilizations self-destruct, we need to understand why and avoid that fate ourselves. If there's a barrier, we need to find it before we waste resources trying to overcome it. And if civilizations choose not to expand, we need to ask ourselves what that means for our own future. But there's another explanation that's gaining attention among scientists. Maybe we're looking in the wrong places, or maybe the signs of alien civilizations are subtle in ways we haven't imagined. This has led to new fields of study like technosignature research, the search for evidence of technology rather than biology. Instead of looking for radio signals or optical beacons, some researchers are looking for signs of massive engineering projects. Dyson spheres, hypothetical structures that surround a star to capture its energy output, would create distinctive infrared signatures. Transit timing variations around certain stars might indicate artificial structures in orbit. Unusual chemical compositions in exoplanet atmospheres could suggest industrial pollution or terraforming. As of 2026, we haven't found any convincing technosignatures, but our search has only just begun, and our instruments are improving rapidly. The James Webb Space Telescope, launched in December 2021, is revolutionizing our ability to analyze exoplanet atmospheres. Future telescopes will be even more capable, potentially detecting biosignatures like oxygen and methane in the atmospheres of Earth-like worlds. This is where interstellar travel and the search for life intersect. Remote observation can tell us a lot, but there's a limit to what we can learn from light years away. Sending a probe, even a tiny one, gives us ground truth. We can measure things directly, see things up close, and answer questions that telescopes simply can't address. For example, if we detected oxygen in the atmosphere of Proxima b, that would be incredibly exciting. Oxygen is highly reactive and shouldn't persist in an atmosphere unless something is constantly producing it. On Earth, that something is photosynthetic life, plants and bacteria that convert carbon dioxide into oxygen. So atmospheric oxygen is considered a strong biosignature, but oxygen can also be produced through non-biological processes. Ultraviolet light from a star can split water molecules into hydrogen and oxygen. Volcanic activity can release oxygen trapped in minerals. Without sending a probe to investigate directly, we can't be certain whether the oxygen is biological or geological in origin. A flyby probe could analyze isotope ratios, measure trace gases, photograph the surface at high resolution, and detect patterns that might indicate life. Even a few minutes of close observation could answer questions that decades of telescope observations cannot. This is why breakthrough starshot matters, despite all its challenges. It represents our best current attempt to bridge the gap between observation and exploration, between wondering and knowing. But let's return to the physics of the journey itself, because there are aspects of relativistic travel we haven't fully explored yet. One of the most mind-bending consequences of traveling at a significant fraction of light speed is time dilation. Einstein's theory of special relativity tells us that time passes differently for objects moving at different speeds. The faster you move, the slower time passes for you relative to someone who's stationary. At everyday speeds, this effect is negligible. Even astronauts on the International Space Station, orbiting at nearly 28,000 kilometers per hour, experience time dilation of only a few microseconds per year. But at relativistic speeds, the effect becomes dramatic. At 10% of light speed, time aboard the spacecraft passes about 0.5% slower than on Earth. That's barely noticeable. But at 50% of light speed, time aboard passes about 13% slower. At 90% of light speed, time passes more than 56% slower, and as you approach light speed, the effect becomes extreme. At 99% of light speed, time aboard passes at only about 14% the rate of time on Earth. This creates a strange asymmetry. Imagine a spacecraft traveling to Proxima Centauri at 90% of light speed. From Earth's perspective, the journey takes about 4.7 years, but from the crew's perspective, due to time dilation, the journey takes only about 2 years. They age 2 years while everyone on Earth ages 4.7 years. Now imagine traveling to a star much farther away. Betelgeuse, the red supergiant star in the constellation Orion, sits roughly 548 light-years from Earth. At 99% of light speed, the journey would take about 553 years from Earth's perspective. But aboard the ship, due to extreme time dilation, the crew would experience only about 78 years. This leads to scenarios straight out of science fiction. A crew could travel to distant stars, spend what feels like a human lifetime exploring, and return to find that thousands of years have passed on Earth. Everyone they knew would be long dead. Civilizations could rise and fall. Technology could advance beyond recognition. They would be time travelers, jumping forward through history with no way to go back. For uncrewed probes, time dilation doesn't matter emotionally, but it does create technical challenges. If a probe experiences significant time dilation, its internal clock runs slower than clocks on Earth. This affects communication synchronization, navigation calculations, and data transmission timing. Engineers would need to account for these relativistic effects in the probe's programming. There's another relativistic effect called length contraction. As you approach light speed, distances in the direction of your travel appear to shrink from your perspective. At 90% of light speed, the distance to Proxima Centauri would appear to be only about half of 4.25 light-years from the spacecraft's frame of reference. At 99% of light speed, the distance would appear to contract to less than 1 light-year. This doesn't change the actual distance, of course. It's a consequence of how space and time are interwoven in Einstein's relativity. From Earth's perspective, the distance remains 4.25 light-years, but from the traveler's perspective, the journey is shorter because space itself appears compressed in the direction of motion. These effects aren't theoretical speculation. They've been confirmed through countless experiments with particles in accelerators, atomic clocks on aircraft, and GPS satellites that must account for both special and general relativistic effects to maintain accuracy. The physics is solid. The consequences are real. But here's where things get truly wild. As you accelerate closer and closer to light speed, another effect emerges: relativistic mass increase. The faster you go, the more energy it takes to accelerate further. At everyday speeds, this is negligible. But at relativistic speeds, it becomes the ultimate speed limit. According to special relativity, it would take infinite energy to accelerate an object with mass to exactly the speed of light. You can get arbitrarily close, 99%, 99.9%, 99.99%, but you can never quite reach 100%. Light itself can travel at light speed because photons have no mass. But anything with mass, electrons, atoms, spacecraft, humans, faces this fundamental barrier. This is why faster-than-light travel, as depicted in science fiction with warp drives and hyperspace, requires physics we don't have. You can't just build a bigger engine and push through the light barrier the way we pushed through the sound barrier with aircraft. The laws of physics, as we currently understand them, forbid it absolutely. That said, physicists are creative, and they've explored theoretical loopholes in the prohibition against faster-than-light travel. The most famous is the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. Instead of moving the spacecraft through space, the Alcubierre drive would compress space in front of the ship and expand space behind it, creating a bubble of normal space-time that carries the ship along with it. From the ship's perspective, it would remain stationary inside its bubble, but the bubble itself would move faster than light. It's an elegant idea that technically doesn't violate relativity, since the ship itself isn't moving faster than light through local space-time. The space around it is moving instead. Think of it like surfing. The surfer isn't moving faster than the wave can travel through water, but by riding the wave, the surfer moves faster than they could swim alone. But there are massive problems with the Alcubierre drive. First, the mathematics require something called exotic matter, matter with negative energy density. We've never observed exotic matter in nature, and we don't know if it can exist in the quantities needed. Some quantum effects, like the Casimir effect, where two parallel metal plates in a vacuum attract each other due to quantum fluctuations, might involve tiny amounts of negative energy, but scaling that up to macroscopic levels is purely speculative. Second, Even if exotic matter exists, the energy requirements are astronomical. Early calculations suggested you'd need more energy than exists in the entire observable universe. Subsequent refinements have brought the estimates down, but we're still talking about energies equivalent to multiple solar masses, far beyond anything humanity could harness with foreseeable technology. Third, there are causality problems. Faster than light travel, even through space-time manipulation, potentially allows for time travel to the past, creating paradoxes. Some physicists argue that the universe has built-in mechanisms, what Stephen Hawking called the chronology protection conjecture, that prevent these paradoxes by making faster-than-light travel impossible in practice, even if it's theoretically allowed. As of 2026, the Alcubierre drive remains a fascinating mathematical curiosity, but there's no clear path from theory to engineering. It may turn out to be impossible for reasons we don't yet understand, or it may require physics beyond our current theories. Either way, we can't count on it for interstellar travel anytime soon. The same applies to other speculative concepts like wormholes, theoretical shortcuts through space-time that could connect distant points in the universe. Wormholes appear in the mathematics of general relativity, but naturally occurring traversable wormholes probably don't exist, and creating an artificial one would require, again, exotic matter and energies we can't produce. So we're back to the hard truth. With the physics we understand and the technology we can foresee, we're limited to slower-than-light travel. That means journeys to even the nearest stars take decades at minimum, and trips to more distant stars take centuries or millennia. This forces us to think on timescales that are uncomfortable for human psychology. We're used to seeing results in our lifetimes. We plan in terms of years or decades, maybe a generation or two, if we're thinking about our children and grandchildren. But interstellar travel requires planning across centuries. The cathedrals of medieval Europe took generations to build. Families would dedicate their entire lives to construction, knowing they'd never see the finished building. That kind of multi-generational commitment is rare in human culture, and it's even rarer in modern times when technology and society change so rapidly. If you are enjoying this, please subscribe to the channel. There's so much more to explore. Join a community that isn't afraid to ask the hard questions about space, technology, and humanity's future. Launching an interstellar mission means committing resources to a project that might not yield results for 50 years or 100 years or more. The scientists who design the mission will be retired or dead before the probe arrives. The funding institutions might not even exist anymore. Political priorities will have shifted. And yet, the mission continues, hurtling through the void with no way to update its systems or change its programming. This is why some researchers argue that we should wait. Technology is improving rapidly. Propulsion systems that seem impossible today might be routine in 50 years. Computing power continues to increase, making spacecraft smarter and more capable. Materials science advances, opening new possibilities for lightweight structures and radiation shielding. If we launch a mission today with current technology, there's a very real possibility that a mission launched 20 years from now with better technology would overtake it and arrive first. This is sometimes called the weight calculation problem. At what point is the technology good enough that waiting no longer provides an advantage? There's no easy answer. If you wait too long, you never launch at all because there's always something better on the horizon. But if you launch too early, you waste resources on a mission that becomes obsolete before it arrives. Breakthrough Starshot represents a middle path. It's pushing the boundaries of current technology while remaining grounded in known physics. It's ambitious enough to inspire, but realistic enough to potentially succeed. And importantly, it's uncrewed. So the risks are purely financial and scientific, not human lives. But even if Breakthrough Starshot succeeds, even if we send probes to Proxima Centauri and other nearby stars and receive data back, we still haven't addressed the elephant in the room. What is the ultimate purpose of interstellar travel? Is it purely scientific curiosity, the desire to know what's out there? That's a noble goal, and it's driven human exploration throughout history. From Polynesian navigators crossing the Pacific in outrigger canoes to astronauts walking on the moon, we explore because we're curious, because we wonder what lies beyond the next horizon. But is curiosity alone enough to justify the immense cost and effort of interstellar missions? Some argue yes, that knowledge has intrinsic value and that understanding our place in the universe is worth almost any price. Others argue that resources would be better spent solving problems here on Earth. Poverty, disease, climate change, environmental destruction. It's a false dichotomy, though. We don't have to choose between exploring space and improving life on Earth. The technologies developed for space exploration often find applications back home. Solar panels, water purification systems, advanced materials, medical imaging, even the smartphone in your pocket, all owe something to space research. Investment in exploration drives innovation across multiple fields. More fundamentally, space exploration reminds us of perspective. The famous pale blue dot photograph, taken by Voyager 1 in 1990 from 6 billion kilometers away, shows Earth as a tiny speck suspended in a sunbeam. Carl Sagan's reflection on that image is worth remembering. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on that mote of dust suspended in a sunbeam. That perspective is humbling and unifying. Our political borders, our conflicts, our divisions all seem trivial when viewed from the cosmic scale. We're all passengers on the same small world, traveling through space together, and that world, as far as we know, is the only place in the universe where life exists, unless it isn't. And that's what interstellar travel could tell us. Discovering life elsewhere, even microbial life, would be the most profound scientific discovery in human history. It would tell us that we're not alone, that the universe is alive in more places than just Earth. It would give us a second data point for understanding how life emerges and evolves, and it would fundamentally change how we see ourselves and our place in the cosmos. Finding life on another world would also force us to confront difficult philosophical and ethical questions. If we discover microbial life on Proxima b, or on the moons of Jupiter and Saturn, or anywhere else, what are our responsibilities toward that life? Do we have the right to study it, to disturb its environment, potentially to contaminate it with Earth organisms? This isn't just hypothetical. Planetary protection, the practice of preventing contamination between Earth and other worlds, is already a serious concern for missions within our solar system. When we send rovers to Mars, they're sterilized to reduce the chance of carrying Earth microbes that could contaminate Martian soil. And when we plan missions to return samples from Mars, we design protocols to prevent potential Martian organisms from contaminating Earth. These protocols exist because contamination could ruin science and potentially cause harm. If we accidentally introduce Earth bacteria to Mars and they survive, we might never know whether life we later discover there is truly Martian or just our own contamination. And while the risk of Martian microbes harming Earth's biosphere is probably low, we can't be absolutely certain until we study them. For interstellar missions, planetary protection becomes even more complex. A small probe traveling at 20% of light speed can't carry much in the way of sterilization equipment, and if the probe is designed to slam into the target planet or moon to release subsurface sensors, as some concepts propose, contamination is almost inevitable. We need to think carefully about these issues before we launch, not after. Once a probe is on its way, traveling for decades through interstellar space, there's no calling it back, no updating its procedures, no changing course based on new ethical considerations. This brings up another dimension of interstellar travel: communication with any intelligence we might encounter. If we discover not just life, but intelligent life, how do we communicate with beings that might be fundamentally different from us? The history of attempts to create interstellar messages is fascinating. The Pioneer plaques attached to Pioneer 10 and 11 in the 1970s featured pictograms showing the location of Earth relative to pulsars, human figures, and the trajectory of the spacecraft. The Voyager Golden Records, launched in 1977, contained sounds and images selected to portray the diversity of life and culture on Earth, along with instructions for playing the record. These messages were optimistic gestures, symbolic rather than practical. The chances of another civilization finding Pioneer or Voyager are vanishingly small. Space is vast, and those spacecraft are tiny needles in a cosmic haystack. But the exercise of creating the messages forced us to think about how we might communicate across the barriers of language, biology, and culture. Mathematics and physics are often suggested as universal languages. Any technological civilization should understand concepts like prime numbers, the hydrogen line frequency, or the value of pi. These could serve as starting points for communication, establishing that we're intelligent and technological beings, but communicating anything more complex, ideas about emotions, art, philosophy, social structures, becomes extremely difficult. Our concepts are shaped by our biology and our evolutionary history. Beings that evolved under different conditions might think in fundamentally alien ways. Consider something as basic as vision. We see the world through eyes that evolved to detect electromagnetic radiation in a narrow range of wavelengths we call visible light. But there's no fundamental reason other beings would use the same sensory modality. They might perceive the world through echolocation, electromagnetic fields, chemical gradients, or senses we can't even imagine. How do you describe color to beings that have no concept of light? Language itself might be radically different. Humans communicate through sequences of sounds or visual symbols arranged linearly in time or space. But what if an alien species communicates through changes in body coloration, like cephalopods, or through chemical signals, like many insects, or through something entirely different? What if their communication isn't sequential at all, but somehow simultaneous or multi-dimensional? These aren't idle speculations. If we're serious about finding and communicating with alien intelligence, we need to think beyond our assumptions. The search for extraterrestrial intelligence has often been anthropocentric, looking for civilizations that use radio waves and laser signals, because that's what we use. But intelligence could manifest in ways that don't produce the techno-signatures we're looking for. Some researchers are exploring the concept of agnostic biosignatures, signs of life that don't depend on assumptions about biochemistry or biology. For example, any life that grows, reproduces, and evolves should produce patterns of chemical disequilibrium, combinations of molecules that wouldn't exist together without ongoing biological activity. Detecting these patterns might allow us to find life, even if it's based on completely different chemistry than Earth life. But we're getting ahead of ourselves. Before we can communicate with alien intelligence, we need to get there. And as we've established, getting there is extraordinarily difficult with current technology. So let's consider alternatives. What if instead of traveling to the stars ourselves, we could bring the stars to us? Not literally, of course, but informationally. What if we could gather enough information about distant worlds that we could virtually explore them without leaving Earth? This is already happening to some extent. Telescopes like the James Webb Space Telescope can analyze the atmospheres of exoplanets by watching how starlight filters through the atmosphere during planetary transits. Different molecules absorb different wavelengths of light, creating a spectroscopic fingerprint that tells us what the atmosphere contains. Future telescopes will be even more powerful. Concepts like space-based interferometers, arrays of telescopes working together to simulate a much larger telescope, could potentially image the surfaces of exoplanets directly. We might be able to see continents and oceans, measure seasonal changes, detect city lights on the night side, and observe weather patterns. With enough data, we could create detailed models of these worlds, virtual environments that scientists could explore from Earth. It wouldn't be the same as being there, but it might be close enough for many scientific purposes, and it would be vastly cheaper and safer than sending physical missions. This raises an interesting question about priorities. If we can learn 90% of what we want to know through remote observation, is it worth the enormous additional cost and effort to send a probe for the remaining 10%? The answer probably depends on what that 10% includes. There are things you simply can't learn from a distance. The texture of alien soil, the microscopic structure of rocks, the presence of organic molecules that don't produce observable atmospheric signatures, the subtle details that might distinguish biological from geological processes. For these questions, you need to be there either with a probe or, ultimately, with human explorers. And there's something else, something harder to quantify but equally important: the human spirit of exploration. We could have studied the moon through telescopes indefinitely, mapping its surface, analyzing its reflected light, modeling its formation, but none of that would have had the impact of Neil Armstrong stepping onto the lunar surface and saying, "That's one small step for man, one giant leap for mankind." Exploration isn't just about gathering data, it's about pushing boundaries, testing ourselves, achieving what seemed impossible. It's about the symbolic value of reaching out beyond our comfortable sphere and touching something new. This is why, despite all the obstacles, research into interstellar travel continues. It's why organizations like Breakthrough Starshot attract funding and talent. It's why scientists and engineers devote their careers to solving problems that might not be solved in their lifetimes. Because the alternative, accepting that we're confined to our solar system forever, trapped on our tiny mote of dust, with no possibility of reaching the stars we see in the night sky, is unacceptable to the human spirit. But let's be realistic about timescales. Even the most optimistic projections for Breakthrough Starshot put a flyby mission to Proxima Centauri decades in the future. First, they need to demonstrate the technology, build and test the light sail, develop the laser array, miniaturize the instruments. Then they need to actually build and launch a fleet of probes, since many will likely fail. Then comes the 40-plus-year journey and the 4-year wait for the signal to return. We're looking at 50 to 70 years minimum from now until we get data back from Proxima Centauri, assuming everything works perfectly. More realistically, accounting for setbacks, funding delays, and technical challenges, we might be looking at 100 years or more. 100 years is a long time. It's longer than most human lifetimes. The people who design and launch the mission probably won't live to see its success. This creates a unique psychological challenge. How do you motivate people to work on a project whose payoff they'll never experience? History offers some examples. The people who planted slow-growing oak trees in medieval Europe knew they'd never sit in their shade, but they planted them anyway for future generations. Scientists who work on climate modeling know their projections extend decades or centuries beyond their own lives, but the work matters because it affects the future. Religious communities have maintained traditions across millennia, Because they believe in purposes larger than individual lifetimes, interstellar missions require that same kind of long-term thinking. They're investments in humanity's future, not in our present. The knowledge we gain, the destinations we reach, the discoveries we make, these will benefit our descendants, not us. This generational dimension adds another layer to the already complex ethics of space exploration. Do we have the right to commit future generations to projects they didn't choose? To spend resources that might be needed for other purposes decades from now? To potentially make contact with alien life or intelligence, fundamentally changing humanity's understanding of itself, without the consent of the people who live through those changes? On the other hand, every generation inherits a world shaped by the decisions of previous generations. We live with infrastructure built by our grandparents, use technologies invented before we were born, inherit both the benefits and the problems created by past choices. Interstellar exploration is just another way that one generation's choices shape the world for those who come after. Perhaps the key is ensuring that these projects serve long-term human interests, not just the ambitions of a few. This is why international cooperation is so important for interstellar missions. A project backed by a single nation or organization could be cancelled if priorities shift. But a genuinely global effort, supported by institutions and agreements that transcend any single government, has better chances of continuity across generations. The International Space Station offers a model. It's a joint project involving NASA, Roscosmos, the European Space Agency, JAXA, and the Canadian Space Agency. Despite political tensions on Earth, cooperation in space has continued for decades. The ISS has been continuously inhabited since the year 2000, surviving changes of government, economic crises, and international conflicts. An interstellar mission would need that kind of resilient institutional structure. But even more so, the ISS orbit is just 400 kilometers above Earth's surface. Astronauts can return home in hours if needed. Supplies can be sent regularly. Problems can be fixed or worked around. An interstellar probe is on its own. Once it's launched, it's traveling for decades through the void, with no possibility of maintenance, repair, or update. Everything must work perfectly from the start, or fail gracefully in ways the designers anticipated. This drives home the importance of redundancy and robust design. Breakthrough Starshot plans to launch not one probe but thousands, a swarm of tiny spacecraft, all heading to the same destination. This redundancy is essential because some will fail. Micrometeorite impacts, radiation damage, manufacturing defects, errors in the navigation system, any of these could destroy individual probes. By launching thousands, even if 90% fail, you still have hundreds that succeed, and those hundreds don't need to all survive the entire journey. Even if only a handful make it to Proxima Centauri and successfully transmit data back to Earth, the mission is a success. This swarm approach also provides redundancy in data collection. Multiple probes can observe the target from different angles, at different times with different instruments. They can cross-check each other's measurements. If one probe reports an anomaly and others don't, you know something went wrong with that probe. But if multiple independent probes report the same thing, you can have confidence the observation is real. The downside of launching thousands of probes is cost. Even if each individual nanocraft is cheap, a few $100,000 at most, thousands of them add up. And then there's the laser array, which is the most expensive component. Current estimates put the total cost of Breakthrough Starshot at $5 to $10 billion. That's a lot of money, but it's worth putting in perspective. $10 billion is less than 2% of NASA's budget over the development period. It's less than what the world spends on pet food in a single year. It's comparable to the cost of a single aircraft carrier. For the first mission to another star system, For answering the question of whether we're alone in the universe, it's arguably a bargain, but money is only part of the equation. Interstellar missions also require sustained political will, public support, and scientific consensus. These are often harder to maintain than funding. Public enthusiasm for space exploration tends to be cyclical. During the Apollo era, space was exciting and commanded public attention, but after the moon landings, interest waned. The space shuttle era saw periods of enthusiasm punctuated by tragedy, the Challenger disaster in 1986 and Columbia in 2003. More recently, we've seen renewed interest with commercial spaceflight, the Mars rovers, and the James Webb Space Telescope. An interstellar mission would need to maintain public interest and support not for years but for decades, through multiple generations. This requires effective communication and engagement. The mission can't just be a scientific endeavor, it needs to be a cultural one, something that captures the public imagination and stays relevant as society changes. Science fiction has an important role to play here. Stories about interstellar travel, from classic novels like Arthur C. Clarke's Rendezvous with Rama to recent films like Interstellar and The Martian, keep these ideas alive in popular culture. They inspire young people to pursue careers in science and engineering. They make the abstract concrete, turning equations and technical specifications into human stories. Education is equally important. The more people understand why interstellar travel matters, what we hope to learn, and how we plan to get there, the more likely they are to support it. This means not just explaining the science, but addressing the bigger questions. Why explore? What will we find? How does this benefit humanity? These aren't easy questions, and the answers aren't always obvious or immediately practical. But they're worth grappling with because they get at fundamental issues of human purpose and meaning. We explore because we're curious, yes, but also because exploration has always driven human progress. Every major civilization in history has been shaped by its explorers. The Phoenicians who sailed the Mediterranean, the Polynesians who settled the Pacific, the Chinese who voyaged to Africa, the Europeans who crossed the Atlantic. Exploration brings new knowledge, new resources, new perspectives. Space exploration is the next frontier. We've explored most of Earth's surface, mapped the continents and oceans, climbed the highest mountains and dove to the deepest trenches, but space is infinite, offering endless opportunities for discovery and growth. What will we find? We don't know, and that's part of the excitement. Maybe we'll find life, simple or complex. Maybe we'll find worlds that could support human colonies. Maybe we'll find evidence of civilizations long gone, archaeological sites among the stars. Or maybe we'll find nothing but rocks and ice and silence, and learn that we're alone. Each possibility teaches us something profound. How does this benefit humanity? In the short term, through technological spin-offs and scientific knowledge. In the long term, by opening new possibilities for human expansion and survival. Earth won't last forever. Our sun will eventually die, expanding into a red giant and vaporizing the inner planets. Even before that, on timescales of millions to hundreds of millions of years, Earth will face challenges: asteroid impacts, supervolcano eruptions, ice ages, or runaway warming. If humanity is confined to Earth, we're vulnerable. All our eggs are in one basket. But if we become a multi-world species spreading to Mars, to the moons of Jupiter and Saturn, eventually to other star systems, then we're no longer dependent on the survival of any single world. We become resilient, capable of surviving catastrophes that would otherwise end us. This is the ultimate insurance policy for the human species. And while it may seem like a distant concern, remember that civilizations think in long timescales. The ancient Egyptians maintained their culture for 3,000 years. Chinese civilization has existed in recognizable form for 4,000 years. If we want human civilization to last for thousands or millions of years into the future, we need to plan for it. Interstellar travel is part of that long-term planning. It won't happen overnight. It won't happen in our lifetimes, but it's a goal worth working toward, a challenge worthy of humanity's best minds and efforts. There's another aspect of interstellar travel we haven't fully explored yet. The question of what happens if we actually find something, not just microbial life or interesting geology, but evidence of intelligence. How do we prepare for that possibility? The search for extraterrestrial intelligence, SETI, has been ongoing since 1960, when Frank Drake conducted the first systematic search using radio telescopes. For over 60 years, we've been listening for signals from the stars, looking for patterns that couldn't be produced by natural phenomena, evidence that someone out there is trying to communicate. So far, we've heard nothing definitive. There have been intriguing signals, like the famous WOW signal detected in 1977, a strong narrowband radio signal that lasted 72 seconds and never repeated. But without repetition or confirmation, we can't conclude it was alien. It might have been terrestrial interference, a glitch in the equipment, or a natural astronomical phenomenon we don't fully understand. The silence is itself interesting and has led to what's called the Fermi paradox, named after physicist Enrico Fermi. The paradox goes like this: the universe is vast and old. Our galaxy alone contains hundreds of billions of stars, many with planets. Even if life is rare, the sheer number of opportunities means there should be many civilizations out there. Some should be much older than us, with millions or billions of years head start on technological development. So where are they? Why haven't we detected any evidence of their existence? There are many proposed solutions to the Fermi paradox. Maybe life is much rarer than we think, requiring such specific conditions that Earth is one of only a handful of living worlds in the entire galaxy. This is the rare Earth hypothesis. Maybe life is common, but intelligence is rare. Earth has been inhabited for billions of years, but technological civilization emerged only in the last few thousand years, a tiny fraction of Earth's history. Perhaps most life remains microbial, never developing the complexity needed for intelligence. Maybe intelligence is common, but technological civilizations are short-lived. They might destroy themselves through war, environmental collapse, or other catastrophes before they have a chance to expand into space or send detectable signals. This is a sobering thought, suggesting that the filter preventing us from seeing alien civilizations might lie in our future, not our past. Maybe advanced civilizations are out there but deliberately hiding, either because they don't want to be found or because there's some kind of galactic protocol against interfering with younger civilizations. This is the zoo hypothesis, the idea that Earth is being observed but not contacted. Like animals in a wildlife preserve, maybe they're using communication methods we haven't thought of or can't detect. Radio waves and laser signals are what we use because they're what we know. A truly advanced civilization might communicate through neutrinos, gravitational waves, quantum entanglement, or something else entirely that we lack the technology to detect, or maybe the distances are just too vast. Even if civilizations are relatively common, they might be so far apart in space and time that they never overlap in detectable ways. A civilization on the other side of the galaxy would be 50,000 light-years away. If they sent a message today, it wouldn't reach us for 50,000 years, and if we replied, they wouldn't get our response for another 50,000 years. That's longer than human civilization has existed. Interstellar travel could help resolve the Fermi paradox. If we send probes to nearby stars and find no evidence of life anywhere, that suggests life is indeed rare. If we find microbial life but no intelligence, that supports the idea that intelligence is the rare step. And if we find evidence of extinct civilizations, ruins or artifacts from beings long gone, that suggests the filter is in the sustainability of advanced civilizations. Of course, there's also the possibility that we find active, ongoing intelligence. This would be the most profound discovery in human history, but it would also raise enormous questions and challenges. First contact scenarios have been explored extensively in science fiction, but reality would likely be far more complex and ambiguous than fiction suggests. We probably wouldn't have dramatic meetings with alien ambassadors or space battles with hostile invaders. More likely, our first evidence of alien intelligence would be something subtle and hard to interpret. A radio signal with mathematical patterns, a spectroscopic signature that suggests artificial activity, unexplained structures on a planetary surface. Interpreting such evidence would be difficult. We'd need to rule out natural explanations, which could take years of analysis and debate. Remember the controversy over the interstellar object Oumuamua in 2017. Some scientists suggested it might be an alien artifact because of its unusual shape and trajectory, but the scientific consensus is that it's probably a natural object, perhaps a fragment of a shattered planet or a chunk of nitrogen ice. If we did confirm that we'd found evidence of alien intelligence, what then? The International Academy of Astronautics has established protocols for what to do if we detect an extraterrestrial signal. The basic steps are: verify the detection, inform relevant authorities and the public, protect the relevant frequencies from interference, and coordinate any response through international consultation. But these protocols assume we're detecting a signal from Earth. Interstellar probes add new complications. If a probe finds evidence of intelligence on Proxima b, we wouldn't know about it for 4 years, the time it takes for the signal to travel back to Earth. And if we wanted to send further instructions or questions, those would take another 4 years to reach the probe, which might have already moved on or run out of power. This communication lag makes real-time interaction impossible. Any exchange of information happens on timescales of years or decades. This is why the probe's programming is so critical. It needs to make intelligent decisions autonomously, without waiting for instructions from Earth. Should the probe try to communicate if it finds intelligence? Should it reveal its presence or observe silently? These decisions have to be made before launch because there won't be time to consult once the moment arrives. Some argue that any probe we send should be purely observational, gathering data without interfering or making contact. This follows the principle of non-interference, similar to Star Trek's Prime Directive, the idea that advanced civilizations shouldn't disrupt the development of less advanced ones. Others argue that if we find intelligence, we should try to communicate. The discovery would be so important that hiding our presence would be a missed opportunity, and if the civilization is technologically advanced enough to detect our probe, they already know we're there. There's also the question of what message we should send if we do communicate. The Voyager Golden Records and Pioneer plaques were created with this in mind, but they're primitive by modern standards. With current technology, we could include much more information, detailed maps of Earth's biosphere, mathematical and physical constants, samples of music and art, even encoded DNA sequences. But we need to be careful about what we reveal. Science fiction is full of stories about alien invasions triggered by humanity broadcasting its location to hostile civilizations. While this scenario is probably unrealistic, the distances are too vast for practical invasion, there's a legitimate concern about revealing too much about ourselves to unknown beings with unknown motivations. Stephen Hawking famously warned against trying to contact aliens, comparing it to when Native Americans first encountered European explorers. The encounter didn't end well for the Native Americans. Advanced civilizations might view us as resources to exploit or threats to eliminate. Other scientists disagree, arguing that any civilization capable of interstellar travel would have long since detected our presence through radio and television signals we've been broadcasting for over a century. Trying to hide now is pointless, and any civilization advanced enough to cross interstellar space probably has resources enough that they don't need to conquer or exploit us. These debates are fascinating but ultimately speculative. We don't know if alien intelligence exists, and we certainly don't know what it would be like if it does. All we can do is prepare as best we can and hope that if the moment comes, we make wise choices. Meanwhile, the practical work of developing interstellar travel continues. Engineers test laser systems and light sail materials. Physicists refine models of propulsion and navigation. Computer scientists develop autonomous systems that can function for decades without human intervention. Materials scientists search for radiation-resistant electronics and lightweight but durable structures. Each advance brings us closer to making interstellar travel a reality. We're not there yet, and we won't be for decades at least, but progress is being made. The question isn't if we'll reach the stars, but when and how, and what we'll find when we get there. As we develop the technology for interstellar travel, we also need to think about the infrastructure that will support it. A single mission to Proxima Centauri would be an incredible achievement, but if we're serious about exploring the galaxy, we need systems that can support multiple missions to multiple targets over extended periods. This means building infrastructure, both on Earth and in space. The laser array for Breakthrough Starshot, for example, wouldn't be a one-time use system. Once built, it could be used to launch mission after mission, perhaps several times per year. The initial investment is enormous, but the marginal cost of each additional launch would be relatively low, mainly the cost of manufacturing the probes themselves. The same logic applies to other components. Telescope arrays for tracking and communicating with distant probes could serve multiple missions. Ground stations for receiving signals could be shared across projects. Manufacturing facilities for producing spacecraft components could operate continuously, benefiting from economies of scale. This suggests that interstellar exploration, if it happens at all, will happen as a sustained program rather than as isolated one-off missions. We'll need institutions that can maintain continuity across decades, funding mechanisms that provide stable long-term support, and international frameworks that allow cooperation across borders. Space agencies like NASA, ESA, and others have experience with long-duration projects. The James Webb Space Telescope took about 25 years from initial concept to launch, surviving multiple delays, budget overruns, and political challenges. The International Space Station has been under continuous development and operation for even longer. These projects demonstrate that it's possible to maintain complex space programs across decades. But interstellar missions are even more challenging because of the timescales involved. A mission to Proxima Centauri wouldn't just take decades to develop. It would take decades to fly there and additional years for the data to return. The total duration from project inception to final results could easily be 75 to 100 years. Maintaining institutional continuity over such periods requires more than just good management. It requires embedding the mission into the cultural and educational fabric of society. The project needs to be more than a government program. It needs to be a shared human endeavor that people feel invested in across generations. One way to achieve this is through education and public engagement. If students learn about the mission in schools, follow its progress as they grow up, and perhaps contribute to it in their careers, the project becomes part of their lived experience. The mission becomes woven into the story of their generation, Universities and research institutions also play a crucial role. Professors and researchers can dedicate their careers to interstellar-related work, training new generations of scientists and engineers who carry the work forward. Research grants and academic positions focused on interstellar topics ensure that expertise is preserved and expanded over time. Private organizations and foundations can provide stability that government programs sometimes lack. Government priorities shift with elections and economic conditions, but foundations established with specific long-term mandates can maintain consistent support regardless of political changes. The Breakthrough Prize Foundation's backing of Breakthrough Starshot is an example of this approach. Crowdfunding and public participation offer another model. While a multi-billion-dollar project can't be fully funded through small donations, public contributions can supplement government and private funding while also building a sense of shared ownership. If millions of people each contribute a small amount and follow the mission's progress, it creates a constituency invested in its success. There's also the question of how we'll receive and process the data when it finally arrives. Imagine it's the year 2075. A probe launched in 2040 has just reached Proxima Centauri and is beaming back its observations. The signal is incredibly faint, taking 4 years to cross the light years between there and here. Receiving it requires massive antenna arrays and sophisticated signal processing. The data itself will be precious. The probe will have only minutes or perhaps hours near the planet before it zips past at 20% of light speed. During that brief window, it needs to capture as much information as possible. Images, spectroscopy, magnetic field measurements, particle detection, everything its tiny instruments can gather. That data, compressed and encoded, gets transmitted back to Earth as a stream of photons or radio waves. By the time it arrives, it's been diluted by the inverse square law, spread across a sphere 4 light-years in radius. The signal strength will be incredibly weak, requiring enormous antennas and long integration times to detect. Once received, the data needs to be decoded, processed, and analyzed. This will be a massive scientific effort, engaging researchers across multiple disciplines. Planetary scientists will analyze surface features and atmospheric composition. Astrobiologists will search for signatures of life. Physicists will examine magnetic fields and radiation environments. Geologists will interpret surface materials and structures. The analysis will take years, perhaps decades. Papers will be published, theories proposed and debated, controversies erupting over interpretation of ambiguous findings. This is how science works, especially with data from unprecedented sources. And all of this assumes the mission succeeds. There's a very real possibility that the probe fails, either during launch, during the decades-long cruise through interstellar space, or during the critical flyby. Equipment might malfunction. A micrometeorite might destroy critical components. The navigation might be slightly off, causing the probe to miss its target. This is why redundancy is so important. Why launching a swarm of probes rather than a single spacecraft makes sense. But even with redundancy, there's no guarantee. The people who design and launch the mission in 2040 may not live to see whether it succeeds in 2075. They'll spend their careers working on something whose outcome they'll never know. This requires a particular kind of faith, not religious faith necessarily, but faith in the value of the work itself, faith that the effort matters, regardless of whether any individual sees the results. It's the same faith that motivated medieval cathedral builders who knew they wouldn't live to see their creations completed, or that drives climate scientists working on problems that won't be fully resolved in their lifetimes. There's something profound and humbling about working on projects that transcend individual lives. It puts our own mortality in perspective, reminds us that we're part of something larger than ourselves, part of a human story that extends backward to our ancestors and forward to descendants we'll never meet. Interstellar travel embodies this perspective. It's not about any one person or generation, but about humanity's long-term journey outward from our home planet, toward the stars that have fascinated us since we first looked up at the night sky and wondered what was out there. This journey has already begun, in a sense. Our fastest spacecraft, Voyager 1, is already in interstellar space, traveling beyond the influence of our sun's solar wind. It's moving at about 17 kilometers per second, fast by terrestrial standards, but glacial compared to what's needed for true interstellar travel. At its current speed, Voyager 1 would take about 70,000 years to reach Proxima Centauri if it were headed that way, which it isn't. But Voyager proves that we can build machines that function in the harsh environment of deep space. Launched in 1977, it's still operational nearly 50 years later, still sending back data, still responding to commands. This longevity is remarkable and bodes well for future interstellar missions. Future probes will need to be even more robust. They'll experience higher accelerations during launch, more intense radiation during cruise, and will need to operate autonomously for even longer periods. But the engineering principles are similar: redundant systems, radiation-hardened electronics, efficient power systems, reliable communications. We'll also learn from missions within our solar system. Every probe we send to Mars, Jupiter, Saturn, or beyond teaches us something about designing spacecraft for long-duration missions. The New Horizons mission to Pluto, for instance, involved a 9-year cruise through the outer solar system, followed by a brief but critical flyby. The lessons learned from that mission about spacecraft hibernation, autonomous operations, and data compression directly apply to interstellar missions. In some ways, we're already preparing for interstellar travel, even though we might not think of it in those terms. Every advance in spacecraft technology, every improvement in propulsion or power systems, every innovation in autonomous navigation brings us closer to making interstellar travel practical. The same is true for our growing understanding of exoplanets. Every new world we discover, every atmospheric analysis we conduct, every planetary system we characterize adds to our knowledge of what's out there and helps us identify the most promising targets for future missions. We're also developing the theoretical framework for understanding life in the universe. Astrobiology, once considered speculative, is now a legitimate scientific discipline. Researchers are studying extremophiles on Earth, organisms that thrive in conditions once thought incompatible with life, to understand the range of environments where life might exist. They're modeling possible biochemistries that don't rely on water or carbon, exploring whether life could be based on silicon, ammonia, or even more exotic chemistry. All of this work, theoretical and practical, is building toward a future where humanity is not confined to Earth but spreads outward into the cosmos. Interstellar travel is the ultimate expression of that vision, the logical endpoint of a process that began when our ancestors first left Africa, crossed oceans, and settled every habitable continent on Earth. But there's an important difference between historical exploration and space exploration. When humans crossed the Atlantic or Pacific, they were traveling to places that could support human life. The Americas, Australia, and the Pacific Islands had breathable air, drinkable water, and ecosystems that could provide food. The explorers could survive with the technology they brought with them. Space is fundamentally different. There's no air to breathe, no water to drink, no food to gather. The radiation environment is lethal. Temperatures range from near absolute zero to hundreds of degrees. Every world we might visit is hostile to human life in ways that Earth's harshest deserts or coldest polar regions are not. This means that human interstellar travel, if it happens at all, will look very different from robotic missions. We can send tiny probes at 20% of light speed because they don't need life support, food, water, or protection from acceleration forces. A human crew would need all of these things and more. The generation ship concept, where multiple generations live and die aboard a spacecraft during a centuries-long journey, is one proposed solution. But the engineering challenges are immense. You'd need to create a completely self-sufficient ecosystem, producing food, recycling water and air, dealing with waste, all while protecting the inhabitants from radiation and providing them with everything needed for physical and psychological health. You'd also need to maintain social stability across generations. The people who arrive at the destination would be the great-great-great-grandchildren of those who departed. They would have grown up knowing nothing but the inside of the spacecraft. How do you ensure they maintain the mission, that they don't decide to turn back or settle somewhere else, that they preserve the knowledge and skills needed to complete the journey? These aren't just engineering problems, they're social, psychological, and philosophical ones. They touch on fundamental questions about human nature, about what people need to thrive, about how communities function over long periods in isolation. Some have proposed alternative approaches. Suspended animation or cryogenic sleep could allow travelers to survive the journey without aging, though we're nowhere near having the technology to make this work. Uploading consciousness into digital form, if such a thing is even possible, would eliminate biological constraints entirely, though it raises profound questions about identity and what it means to be human. More realistically, the first interstellar travelers might not be human in the traditional sense, but rather post-human, beings who have augmented themselves with technology to survive in space environments. Cybernetic enhancements, genetic modifications, or integration with artificial intelligence could make interstellar travel more practical, but these possibilities lie far in the future, if they're possible at all. For now, our focus is on robotic missions because those are what we can actually build with foreseeable technology. And even those face enormous challenges, yet despite all the difficulties, despite all the unknowns and uncertainties, progress continues. Engineers keep designing better spacecraft. Scientists keep discovering new worlds. Computer scientists keep developing smarter autonomous systems. Materials scientists keep finding stronger, lighter, more radiation-resistant materials. Each small advance contributes to the larger goal. Breakthrough Starshot aims to send its first probes within the next few decades. Other projects, like Project Dragonfly, proposed by the Initiative for Interstellar Studies, are exploring alternative approaches. Government space agencies are beginning to take interstellar travel seriously, funding preliminary studies and technology development. The momentum is building. What seemed like pure science fiction a generation ago is now being seriously discussed in scientific journals and planning documents. We're transitioning from whether to how and when. This transition matters because it represents a shift in humanity's relationship with the cosmos. For all of history, the stars have been distant, like beautiful but unreachable. We could observe them, study them, wonder about them, but never visit them. They were the ultimate frontier, forever beyond our grasp. Interstellar travel changes that. It makes the stars not just objects of study but destinations, places we can actually go, even if the journey takes decades or centuries. This transforms the universe from an abstract concept into something tangible and accessible. It also changes how we think about our place in the cosmos. Earth is our home, our cradle, but it doesn't have to be our prison. The universe is vast beyond comprehension, containing billions of galaxies, each with billions of stars, many with planets. Some of those planets might harbor life, Some might be capable of supporting human colonies. Some might be home to civilizations far older and more advanced than ours. We don't know what's out there, and that's exactly why we need to explore. Every great discovery in human history has come from venturing into the unknown, from asking questions whose answers weren't obvious, from taking risks in pursuit of knowledge. Interstellar travel is the ultimate expression of that exploratory impulse. It's humanity at its best, curious, ambitious, willing to undertake enormous challenges for the sake of discovery and advancement. It's also humanity acknowledging our limitations, our mortality, our smallness in the face of cosmic vastness, yet choosing to reach for the stars anyway. The journey won't be easy. It will take decades of work, billions of dollars in funding, international cooperation on an unprecedented scale, and sustained commitment across multiple generations. Many challenges remain unsolved. Some may prove insurmountable with current technology, requiring breakthroughs we can't yet imagine. But the same was true of every great achievement in human history. Flight was impossible until the Wright brothers made it possible. Space travel was fantasy until Gagarin and Armstrong made it reality. Exploring the solar system was science fiction until Voyager, Cassini, and New Horizons showed us the wonders of distant worlds. Interstellar travel is the next step in that progression. It's the challenge that will define this century, and perhaps the next, a goal worthy of humanity's best efforts and highest aspirations. Whether we succeed or fail, the attempt itself will drive innovation, inspire generations, and expand our understanding of what's possible. And someday, perhaps in your lifetime or perhaps in that of your children or grandchildren, we'll receive a signal from a tiny spacecraft at Proxima Centauri. The data will be analyzed, revealing what that distant world is really like. Maybe we'll find signs of life. Maybe we'll find a dead world, barren and lifeless. Maybe we'll find something we never expected, something that challenges our assumptions and opens new questions. Whatever we find, it will mark a turning point in human history, the moment we first reached beyond our solar system to touch another star. It will be the beginning of humanity's true journey into the cosmos, a journey that may one day see our descendants spreading throughout the galaxy, exploring worlds we can barely imagine, and perhaps encountering others who, like us, looked up at the stars and wondered, what's out there? That question has driven us from the beginning, and now finally we're developing the means to answer it. If you found this fascinating, click the video on the screen. We cover all the reasons we can't survive interstellar travel, because we've talked about the incredible possibilities. But what about the physical, biological, and psychological barriers that might make human interstellar travel fundamentally impossible? You don't want to miss this one.